Welcome to this video on K-nearest neighbors regression. This is a foundational topic in instance-based learning for anyone studying AI and machine learning. We begin with Section 01, Fundamentals, where we will explore the core intuition, mechanics, and the memory-based learning paradigm of KNN. KNN is a non-parametric lazy learner, meaning it stores the training data and computes predictions at runtime. This contrasts with parametric, model-based algorithms like linear regression, which learn a function and discard the training data after. The core intuition of KNN regression is proximity, or local averaging. The hypothesis is that points close in feature space likely have similar target values. In regression, we find the K closest neighbors and average their output to predict a continuous value. Next, we move to Section 02, the mechanics, covering essential components such as distance metrics, weighting, and hyperparameter tuning. Selecting the right distance metric is crucial. Common choices include Euclidean distance for continuous data, Manhattan distance for high-dimensional or discrete data, and Minkowski, which generalizes both. The choice of $k$ determines the bias variance trade-off. As $k$ increases, the model becomes simpler, leading to higher bias but lower variance. We must choose an optimal $k$ to balance these trade-offs. Weighting strategies define how neighbors contribute to the prediction. Uniform weighting gives all neighbors equal influence. Distance-weighted decreases influence as distance increases, and kernel-based methods use specialized functions for smoother proximity curves. KNN is non-parametric, assuming no functional form, making it flexible. Linear regression, in contrast, is parametric, assumes a linear relationship, and is much faster for predictions. A major challenge for KNN is the curse of dimensionality. In high-dimensional space, data becomes sparse, making distance metrics less meaningful. This requires exponential data growth to maintain density and predictive power. To ensure robust KNN performance, always use feature scaling to prevent larger scales from dominating. Implement feature selection to reduce dimensionality and speed up runtime. Finally, utilize cross-validation to find the optimal $k$ and weighting scheme, and use spatial indexing for efficiency with large datasets.